fracturing as well as sand identification, formation identification. When we drill vertical wells in Pennsylvania, my job is usually just involving the geology, sand description. In New York, the wells are typically smaller, easier to drill. Often they're running to drill. That's the background I come from. Graduate geologist, I've been doing well supervision, water wells, gravitation, you name it, for 20, 30 years. Almost a lifelong resident of this area. I grew up in Truth. Anyway, this evening we're going to talk about drilling as it's done in this area. We're going to talk about fracking, and then I want to, after we let Tom Shepstone from Pennsylvania do a little talking about their economics and roads and so on there, I want to come back and finish up discussing some of the problems and perceived problems. Roads, radioactivity, water disposal, that kind of thing. I think the best way to approach this is let me ramble on for half an hour or 45 minutes, and then if I don't adequately explain something, feel free to ask some questions. To get started, I'd like to point out that drilling and fracturing, hydraulic fracturing, we're going to use that term interchangeably here, are two distinctly different events. Drilling is putting a hole in the ground. Fracturing requires the hole in the ground, but you can complete a gas well or an oil well without fracturing it if it encounters what you want without fracturing. The fracturing by design is to stimulate production, get the rate up to where it's economic. That's what a fracturing job is designed to do. You can fracture rock, crack rock, that's really what we're talking about, a number of ways. If you like a little more excitement in your life, you can do it with explosives. The old days, we shot a well with explosives last fall, an oil well, down in western New York. The penetration of the cracks propagated in a shot situation are probably out of the order of 10 feet. And we know that partly from production characteristics and also from running what we call caliper logs in the wells after we've shot them, after we clean them out. The reason the industry has gone to hydraulic fracturing, and hydraulic fracturing is simply the pumping of a fluid. And you can pump any fluid, any kind of a liquid. Hydraulic fracturing works basically the same as the hydraulic system in that tractor back there. You build pressure on the surface, pump it through a pipe down a well to where you want to break something, and if you build enough pressure, something will fail, something will break. Hopefully it's the rock that you intend it to be, and that crack propagates back into the formation. That's the plan, that's a desire. And we also, in a gas well fracturing or oil well fracturing job, we want to place some sand. I got a container here of frac sand. If you look at this closely, and you were at Bill Capel's speech a couple of weeks ago, you'll notice this sand is coarser. And there's different gradations depending on what you're trying to do. In a conventional vertical well, the goal used to be, and still is for the most part, we want to make a crack 5 sand grains wide. And the reason for that is that's to be the conduit back to the wellbore as well as the production face. When you drill a hole in the ground, 6, 8, 10 inches in diameter, whatever it is, the circumference of that hole times the height of the formation is the productive face. If you propagate cracks, one or more, back away from that wellbore, you then expand the productive face into that well hundreds, 1,000 times, and some of those cracks go in a nice straight line, some of them intersect pre-existing cracks, tend to follow them, some of them propagate new cracks. And the goal is to drain the rock formation. And we're talking about a hard rock. I brought along a little of the Marcellus here. Bill Capel had some core pieces. This is what the Marcellus looks like from 10,000 feet, 5,000 down, 5,000 over, from a well in northern Pennsylvania. It's typical black shale. This is what I get to see after I wash it out of the drill cuttings. So it's nice to say it's black shale. We can describe the carbonate content, see how hard it is, see how it breaks, that sort of thing. But most of the analysis of the shales comes from the actual fracturing and the results, the hydraulic results that it produces. Now, let's take a look at our area. Anybody that's been to any of these talks in the past has probably seen some version of this map. This is right out of the New York State Draft Environmental Impact Statement. The original version is color. I'm too cheap. I made a black and white version. Pennsylvania, New York line, Lake Erie, Syracuse is up here. We're right here. And I've added a few things that aren't on the New York DEIS version, and we'll come back to that in a moment. When in this county we have probably 100 gas wells already. They're situated up here in the north end, in the vicinity, town of Fayette area, and you drive any of the main roads, you can look out across the fields and you'll see usually a tank and some assorted plumbing beside it. To drill a well in New York, the first thing we need to do is drill a bedrock. In this particular area, a lot of you guys farm, you know, you don't have to go too far to bedrock, 10, 15, 20 feet or even less. Whatever depth it takes, we want to get to bedrock. Same as if we drill a water well in your yard. And the purpose of that casing, that first casing we're going to put in the ground, is to simply hold the well open, to keep the dirt, the gravel, till, whatever you got, out of the well bore, and we want to seat that in solid rock, just exactly the same as your water well. Then your water well contractor drills inside to whatever depth he has to go. Hopefully you find some water, and you're in the water business. When we're drilling a gas well, we want to get out of the water business. We're looking for gas, obviously, or oil. We start out the same way. We set conductor to bedrock. Then the state of New York requires a minimum of 450 feet of surface casing, of water string casing. It either has to be to 450 feet or 75 feet below the deepest freshwater zone, whichever is deeper. And there are some situations where it's actually less than that, but they're dictated by the local geology. The first casing can be driven into the ground. If you drill a hole bigger than the casing and you set the casing in, it has to be grouted. It has to be cemented around the outside. However, if you drive it, what we call drilling and driving, the old-fashioned cable tool rigs drove them into the ground. We now have modern rigs that are capable of drilling inside and turning the casing at the same time. We put some carbide buttons on the bottom of the casing and drill as deep as we like. Conductor's pretty easy to set in most of the town of Covert because the depth of rock isn't very deep. Go drill in downtown Ithaca, you may put in more than 500 feet of conductor to get to bedrock. Same is true of Watkins Glen and in the lake valleys. Once you get to rock, then we've got to set our water string 75 feet below the deepest fresh water. State rules, this has got to be cemented in. And because we've drilled inside the larger diameter hole, we now have a space in between this casing that we've got to run and the hole. This is called the annulus. We've got to fill this with cement. We do that by pumping cement down the inside and circulating it back up around the bottom, all the way back to the surface. If it does not come back to the surface, we're going to be obligated to pour some in from the top. we circulate usually 50% excess of the calculated volume to help ensuring that it makes it back to the surface. If it doesn't come back to the surface, you're also obligated in most situations to run a bond log, which is a run on a wireline truck. It's another $5,000–6,000 of expense that you don't want. Cement's a lot cheaper. We want to cement this guy in. That's our goal. Then, typical Medina well, you're off to the races drilling. You can drill as deep as you like. Most of the wells in the north end of this county, a couple thousand feet deep, more or less. You have two options. You can stop. We need then to run one more string of casing, because at this point you've got a long well bore full of open hole rock. We want to contain the gas, get it to the surface where we can sell it. We run a production casing. Typically this stuff right here, 4.5 inches in diameter. It either goes through the zone of interest, and then if this is our zone of interest, we're drilling down here. We run the casing through, same deal. We got to cement him again. We pump cement down the inside, back up around the outside. Some areas of the state, we don't want the cement to come to the surface, but in most areas we do. And so we want to completely fill this void, this annular space outside the casing. The demonstration right here, these annular spaces are not big enough. State law requires a minimum of almost 2 inches depending on the casing size, and there's actually a chart for that. Once you've cemented this guy in, we've then got to shoot holes in him. We literally go in on a wire line with shaped charges, and we shoot a hole through the casing. It makes a hole exactly the size of that pencil, believe it or not, and I've actually had to fish them out of wells to look at them. They're just like a bullet hole, right through the casing. Then, if the formation will give you whatever fluid, whatever gas it's got, that's good enough. It'll come through the perforations, flow to the surface, you're in business. Most rocks in New York will not. That's where the frac job comes in. In a vertical situation, you'll typically have 50 feet or less of formation exposed in the wellbore, holes through the casing. The frac job is then, we hook onto the top of the casing, appropriate valves and pumps, pump fluid down, out through the holes, into the formation. We literally exceed the breaking strength of the rock, either propagate new cracks or open up existing cracks. The reality is it's a combination of both. And when we get done, we want to fill that crack 5 sand grains wide with this stuff. And so typical vertical well frac job takes a couple hours in the morning, takes longer to set up and rig down, and they're gone. $30,000 and goodbye. And then at that point you're left with a hole full of fluid. You got to unload and produce whatever the frac job encountered. That worked pretty good for a long time, continues to work. A little bit of history here. About 10 years ago, natural gas was starting to get short supply. Price was going up. The minute, it's no different growing corn or milk or anything else. What happens when the price goes up? People start thinking of ways to grow a little more, produce a little more. The industry continues to explore for new reserves, because in the gas, in the petroleum business, you continually produce yourself out of a job. There's only so much finite reserves that you're going to produce. As you produce them, at some point, if you want to stay in business, you've got to go find some more. You've got to drill another well or a series of wells. 10 years ago, in this yellow area right here, Chemung and parts of adjoining counties, the Trenton Black River Formation, depths typically 5,000, 6,000, 7,000 feet below the surface, was drilled and found to have natural gas in zones that were specifically defined by seismic modeling. Seismic crews run up and down roads, put out a bunch of sensitive geophones, bounce some kind of shock waves generated by explosives or or vibration, and the interpretation of that defines targets that we want to drill through. The initial Black River wells were actually vertical holes, and the industry said there's a better way to do this. We want to go through those, for the zones of interest, which are actually fault plains, we want to go through them horizontally. So the horizontal industry came to New York. Horizontal drilling isn't new. It's been around for 20 years, but its application on land in the northeastern U.S. is really new in the last decade. Anyway, when we start out to drill a horizontal well, we do it exactly the same as a vertical well. We start out with casings. We still have to comply in New York with the minimum 75 feet below the deepest fresh water. The fun part about drilling to the Trenton Black River is we have a couple of zones on the way down that give us a little trouble. And trouble is spelled salt. And immediately below the salt beds, we have a water-sensitive shale. And so if you can drill them dry, there's no problem. If you drill with compressed air, no problem. They drill, they stand up very nicely. You can drill as deep as you want to go, wherever. If you get them damp, you get them wet, the salt will dissolve, make an oversized cavern, stuff starts to collapse. If you're drilling in a water, any kind of a water-based fluid, or the hole's making any water, the water-sensitive shale underneath wants to fall in on you, grab you, collapse the hole. The fun starts. So typically, what we do to deal with that is we run another string of casing through these zones that give us trouble, the salt and the underlying shales. So to drill a modern ultimate, starts out vertical, then goes horizontal. We start out with bigger casing because we need to run more of them. And each time you run a string of casing, you can see here, they step down. We've got to go smaller. I've even brought along a little bitty drill bit. He goes right in there just nicely. I can't pick up the big ones, so I can't show them to you. But typical horizontal well starts out with like a 20-inch diameter casing. If you have the right drilling equipment, you can literally screw it in the ground. In the same way we drilled this conductor here, we're putting it in for the same purpose, get to bedrock. Hold the soil, the till, the rock open in anticipation of going deeper. If we can't turn it in or can't drive it in, driving big diameter pipe's hard to do. It likes to buckle. It doesn't cooperate like little stuff does. One way or another, we got to get that big conductor to bedrock. If there's any void space, any annular space on the outside, we got to cement that. Then we still have to contend with fresh water. And if we do it in New York, we've still got our minimum 450-foot rule, or 75 feet below deepest fresh water. A number of companies elsewhere in the world will make this 10% of the anticipated total depth. And so if I'm drilling a 5,000 or 6,000 foot horizontal Black River well, I may make the water string 600 feet long. But I got to have a minimum of 450 under present New York rules. Once I run that in, I got to cement that same way. In this sketch right here, it's 13 3/8 inches in diameter, standard oil field size. Then I'm off drilling. I can drill as deep as I want to go inside there with a 12.5-inch bit, and we typically do that through what we call the Vernon Shale, the water-sensitive shale. In the case in this area of southern New York, 4,500 feet, something like that. This stuff weighs 36 pounds to the foot. It takes a little bit of a derrick to pick it up and plunk it in there. And same deal, it's got to be cemented. So we circulate cement down the inside. Some of these cement jobs can exceed 1,000 sacks of cement and you mix a sack with 6.5 gallons of water, 5.5 to 6.5 depending on the additive. So the cement jobs are a big deal. Any of you that have poured cement, and we're standing on a floor covered with it here, know that it'll set up in a couple of hours. Normal Portland has a gel time. In order to physically get this stuff in the hole, to pump it in at 100 or 200 gallons a minute, we have to calculate the time it's going to take for it to set. We sometimes add chemicals that either retard the set or advance it. Portland cement has another bad habit. There's an extended transition period from when it goes from a liquid to a solid. Now, and in this situation, I'm talking about cement with no aggregate in it. We're talking about what we call neat Portland cement, and we pump the stuff. So we have to deal with the chemistry of the cement. To get back to the transition business, if I've got a long column of cement here, and the cement here is represented by the hatchered zones on each side of my casings. The cement column needs, number one, needs to circulate all the way back to the surface and needs to set. I've got to be able to pump it and get it to where I want it before it'll gel, before it sets. If the transition time is too long, anything that's out here in that hole that has some gas or some oil or some water into it, when it's in the transition phase, as it's going from a liquid to a solid, it doesn't exert any hydrostatic pressure. Hydrostatic pressure is the weight of a column of fluid, and fresh water is 0.43 psi, almost half a psi, for every foot in height. And so if I'm down here 5,000 feet, I've got better than 2,000 psi of pressure in this cement column outside the casing. Right at the point where that cement gels, it no longer exerts that pressure. That's the point at which cement can be channeled if we don't do something about it. And we do. We add a bunch of additives to shorten the transition period and try to ensure that that cement won't leak, won't be a problem somewhere down the road. Once we've done that, we've got our salt section behind us. We can go on. We drill as far as we want to go vertical. We get to what's called the kickoff point. We then are going to turn to horizontal. You take, this guy looks pretty rigid. You get him 40 feet long and you suspend him on both ends here across this shop, he'll droop. And steel casing, steel drill pipe has got to be able to go around this curve, and you've got to do it within the elastic limits of the steel, because we're going to turn, we're going to eventually run production casing around here, but in the meantime we've got to be able to turn rotary drill pipe around here. When we're building angle, we start out to build this angle. Incidentally, the radius on this circle is 500 or more feet, the radius. So to get around the bend, it's about 700-800 feet around the bend, or more, depending on how you design the well. Steel will track around there. When we're setting out to build the curve, we actually use a bent drill string, typically about 2 degrees bend. And we have a bit like this. He's larger than this. There's a couple of different kinds of bits we'll discuss here in a second, but we have a bit on the end. Behind that, we have a motor. The motor is actually a turbine, and we pump fluid down the center of the drill pipe that's connected all the way down to this motor, and we can either turn the drill pipe if we want to go straight. If we want to bend, we just hold the drill pipe oriented in the direction we want to go, and we spin the motor by pumping fluid. And we can build about 8 degrees of angle per 100 feet of digging. You can actually get up around 10 or 12 if you're approaching the elastic limits, and sometimes things don't always behave quite the way you want them, so you want a little margin for error in all of this. At any rate, to build angle, we don't turn the drill string. We simply pump down it. We orient the bend in the direction we want to go. We build the angle. Once we've got the angle built, then we've got to stay in the formation. Well, I worked on a formation here a couple of months ago that was only 10 feet thick. I'm going to tell you what, trying to make this guy go half a mile in a zone that's less than the height of this room is not quite as easy as it sounds. If the formation you're in is as flat as this floor, there's no problem. If he wanders around very much, it's a big problem. But anyway, let's in the Black River, we typically were looking at a target that was 40 or 50 feet high. Wasn't too serious a problem steering. We didn't have too much trouble staying in the zone. There, we were encountering features that we had defined by seismic and knew approximately where they were. All we had to do was drill through them, get to the end of the hole wherever we planned to go, and then we run 10, 15,000 feet, whatever there is of this stuff, one joint at a time, screw it all together, down the hole we go. Cement it in. Same deal we do every time. Pump cement down the inside, back around all the way. Lots of times they don't bring the production string back to the surface because you run out of time pumping the stuff. And there are even ways to have tools that out in the casing string that will open, allow you to pump a second string of cement if necessary. Adds to cost, complexity, more things to go wrong, but it can be done. Then all we have to do, let the cement set. If we know where our faults are, the features that we want to attack, we simply shoot holes in them. If they're sufficiently porous and permeable to produce gas, drilling's done. We don't have to frack. Sometimes they get cleaned up with a little hydrochloric acid. A little hydrochloric's 10,000 gallons. In fact, if this casing is 5.5 inches in diameter, which is a popular size to go down and around, if it's 10,000 feet long, it takes almost 10,000 gallons of fluid just to fill the casing. So we deal with big volumes of stuff. This went on for 3 or 4 years in the early 2000s. There's still an occasional well drilled in the Black River, but basically the industry moved on. Natural gas production soared in the Chemung County area for a few years as a result of this. At the same time, the Marcellus play in Pennsylvania got going. The application of horizontal drilling and combined with fracturing was found to be successful in producing the Marcellus. As you can see, the Marcellus is just a black shale. Bill Capel had some, if you were at his meeting the other night, just a black rock. Not very exciting looking stuff. We do exactly the same thing over the border in Pennsylvania. I've spent a good deal of time in Bradford County, but it's the same area, same game throughout. We start at the top, set our successive casings through fresh water. Down there, we actually set a double string of casing, which isn't required, but the industry has done that in an attempt to generate a greater safety factor, if you will, for lack of a better term. The second casing being about 1,000 or 1,200 feet long. First casing is typically as deep or deeper than any known freshwater wells in some radius, often half a mile or more from the well bore. They're all cemented in the same way. Marcellus drilling, once you've got your intermediate casing set here, 1,000 feet, whatever it is, the rest of the shales are pretty easy to drill. If you drill to your kickoff point, you go around the curve as far as you can go, depending on your lease ownership. If you look at these things in map view, there are some practical limits to drilling, but if you go straight away from a well pad, go straight down, straight away. You can go 10,000 or more feet, no problem. And when I say 10,000 feet now, I'm talking about what the industry calls vertical section. This is from the position of the well bore to the end of the well. That doesn't count the first mile getting down there. This is just the horizontal distance away. Once you get down here, you don't start producing until you get into the formation after pretty near or at the bottom of what we call the landing point. You're pretty well around the turn into the zone that you want to be in. Now, because this length can be long, somewhere between 3,000, longest one I've ever been on was 8,400 feet. But the industry is capable of twice that if you own enough acreage. Biggest problem is, I shouldn't call it a problem, the constraining factor in a lot of this is how much lease land, how much mineral rights do you control that you want to drill. There are some practical limitations to how far you can go depending on how flat or how consistent this formation is. The problem being the drill string is quite thick, it's quite stiff. I mean, this stuff doesn't bend very readily. We can make it go up and down, but we only change a few feet in for every 100 that we drill. It's kind of like landing the space shuttle. You only get one shot. You can't stop and jack it up or down. You're committed. Get our lateral, whatever depth we're at. We then break the lateral up into segments. And when people talk about massive hydraulic fracturing, that's a bit of a misnomer because yes, we're going to use a lot of fluid in total, but in each what we call stage, we typically divide the well bore up into 300 or 500 foot increments. And there's ongoing discussion, ongoing research as to what the optimum stage is. And they'll probably be discussing that as long as they drill horizontal wells and frack them. But at any rate, we then set out to frack, to stimulate a specific stage. We've got to isolate that stage in the well. We do that with packers, which are nothing more than a giant balloon that we inflate. We also can do it with baffles, which are nothing more than a retainer that catches some kind of a plug or a ball. We've got a number of gadgets to isolate zones, and they're dreaming up more all the time. We hook our pump trucks on the surface, pump our mixture of fluid, usually water. We pump down some sand. A lot of the frac sand used in shale wells is actually finer than this. We got to have some holes through this casing that we ran in here after we drilled the hole. We shoot the holes, isolate the zone, and frac it. Typical stage, depending on how vigorously you want to attack this formation, something on the order of 100,000 gallons. It can vary all over the map. It can vary from much less than that to more than that, depending on what you think you're trying to do. Bill Capel showed a slide from USGS research where they demonstrated that if you continue to pump on a zone and it found a way weakness, it would leave the formation that you're trying to frack and usually grow upward. Pressure goes in the direction of least resistance. It doesn't care which way it's going. Whichever way breaks first, that's where it's going. Some of the frac jobs in the deeper wells, southern Pennsylvania and West Virginia, they've actually documented that it can climb as much as 1,000 feet. That's not a desirable thing. For number one, people worry about where it's going. Also, you just wasted a bunch of sand and water and energy and time fracking something that isn't going to give you anything to sell. The goal is to stay in this horizontal zone, in this layer of rock. And so the well is then fracked in successive stages all the way back till you're done. At that point, you wind up with a hole full of fluid. Sometimes they'll unload themselves. Sometimes you've got to go in here with tubing and blow some of the water out to get the gas. Gas wells flow by gas expansion. Pressure drive to the wellbore. The gas flows to the surface if it can overcome whatever pressure is in the wellbore. And so sometimes you have to get some of the fluid out of here in order to get the gas coming. All the mechanics of drilling, it's basically the same game every time. This is the pretty standard procedure for horizontal drilling. The reason why the Marcellus was attractive in northern Pennsylvania was the thickness. I've added some numbers here. 30 years ago, we looked at the Marcellus in Allegheny and Steuben and Chemung counties as a part of the Eastern Gas Shales project. I worked out about 6 of the 8 wells that were drilled back then. They were all fracked. They were vertical holes. We fracked the black shale. They all produced gas. Most of them didn't make enough gas to pay for the frack job, never mind the drilling or anything else at the time. But they did produce. We demonstrated that the process works. We just couldn't do it economically. And so that languished until somebody came up with a bright idea to combine the horizontal drilling, which exposes considerably more of the wellbore, to our ability to frack. Ideally what we want to do, you go back to plan view, we've got our horizontal wells drilled, excuse me, 1 or more. This spacing between wells is usually on the order of 600 to 800 feet. And we more or less want to maintain that spacing. The reason being, we believe in each one of these stages that we're going to propagate here, we can effectively produce cracks laterally about half that distance, 300 to 400 feet. In other words, we can go halfway to the adjoining well. If we go too far, we generate too much communication. We want to adequately drain. We don't want breakthrough from one well to another. We want cracks to go out here to allow the gas then to feed back to the wellbore. And that's our goal, maximize our recovery. So, pretty much standard procedure. In New York, we believe we can do the same thing in the Marcellus. We haven't yet tested it. Back to this map from the generic environmental impact statement. There's a line that shows up on this. I've highlighted it in blue. This is the top of the Marcellus being 2,000 or more feet below the surface, anywhere south of this line. The reason for that is the state has decided, and this is an arbitrary line, but we've decided that we need our 450 feet of water stream protection going down. We want more than 1,000 feet of spacing between that and the top of any fracturing that we believe will happen. So we arbitrarily generated this 2,000 foot. This is proposed now for new regulations. This is not yet rule, but will be, or some variation of it will be, if the state decides to allow horizontal fracturing of shales. So as you can see, that basically is just the southern row of counties in New York. I'm telling you that over here, the formation isn't very thick. The Marcellus is actually divided into 3 parts. We typically frack the lower third. It's called the Union Springs unit, which is the bottom of the Marcellus. Steuben County, it's about 13 feet thick. South of Watkins Glen, it's about 44 feet thick. Get down here in central Tioga County, gets up to 70 feet thick. It's getting thicker going this way. Bradford County, Pennsylvania, 120 or more feet thick. So, making the judgment that the thicker the formation is, the more gas or oil it's going to have in it, where do you want to drill? This is the attraction for going south. I think that even if New York removes the moratorium and says, yes, you can drill, the only areas that will really be of interest will be Chemung, Tioga, and Broome counties. Now, it's thick over here too. This dark smudge is the New York City watershed area. So, politically, you're not going there. It also happens to coincide with the Delaware River Basin. The Delaware River Basin is governed by, in part, by the Delaware River Basin Commission. There's also a Susquehanna River Basin Commission that deals with everything. Right here, essentially south of Newfield, is the Continental Divide. Water north of there flows north, water to the south flows south. Anything that flows south is in the Susquehanna River Basin Commission. They govern water usage, water withdrawal rates, and they regulate withdrawal sources, anything bigger than a residence. And the Delaware River Basin Commission does the same thing. They've gone on record as saying they're not going to allow drilling, period. Now, that may change, but it's not going to change anytime soon. So basically, in New York, we're just dealing with this area as far as the Marcellus is concerned. Now, the Marcellus, when we drill a well, we log. I talk about wireline logs, that sort of thing. Brought one along here. The little red mark, this is every 2 inches here is 100 feet. The little red mark up there near the top is the Tully limestone. That's the formation, that's the caprock of the lower falls at Tagana. If you drive down Route 89, look at the lower falls, you're looking at the Tully limestone. That little hard layer right there that you can see right from Route 89. The Marcellus is the next blue layer down, where I've got the little blue stuck there. This incidentally is from just south of Watkins Glen, this particular well. Then we come way down here, just above the floor is the Utica. And everybody's heard about the Utica shale. It's a little thicker than the Marcellus, not a lot. It's about half as organically rich. Now, if you look at the Marcellus, look at unconventional, what we call unconventional gas sources, there are a number of areas in the country where they are being explored, produced. This is South Dakota, the Bakken area. It goes up into Canada. The Marcellus and the Utica areas almost overlap, not entirely. The Utica extends farther into Ohio than does the Marcellus. The Utica is also present up in the St. Lawrence Valley. Up here it has been fracked in a few exploratory horizontal wells. It produced gas, but the initial rates were like 1 million cubic feet a day. That sounds like a lot. It's not. The rates we're getting down here are 5 or 10 times that initial open flows. So there has been some exploration of the Utica in New York. At this point, it's more of an unknown. We talk about drilling it. Most of us won't live long enough before we see very many Utica wells drilled in New York. And I'll come back to that in a moment. But there's a lot of rock between the Marcellus, which is relatively easy to drill, and the Utica, which is a little more problem. We got our salt section here again. We got to run another string of intermediate casing. A lot more expensive drilling, time consuming. In Pennsylvania, we've gotten to the point, it's almost unbelievable. Little rig sets the 20-inch casing. Big rig comes in and drills to the rest of the well from 100 feet to 10,000 or more, 12,000, some of them even 14, depending on surface elevation. Last one I was on was 11 days. And that includes setting 2 strings of pipe and waiting 8 hours for the cement to set. When you're drilling this stuff at 300-400 feet an hour, it gets pretty frantic if you're trying to look at samples or steer the thing. It used to take up to a month. I can remember working on a Black River well in Chemung County. I was there 60 straight days. We had some trouble. We had some drilling issues. It was not a trouble-free well. But the industry has learned to do things quite a bit faster and hopefully not sacrifice quality in the process. What that's done is reduce the cost, and that's necessary because along with this glut of gas, the price has gone down. Same thing growing corn, soybeans, anything else. Grow too much of it and see what happens to the price. Same problem. You're treating them as a commodity. In Pennsylvania, they're pushing 6,000 horizontal shale wells in the last 5 years, and they're roughly evenly divided between the northern area and the Pittsburgh area, which on this scale map is southwest corner. There's a scattering of wells in between, some of which have a little production history, some don't. There are 2 or 3 wells that were drilled just south of Olean recently. Pretty interesting to see what they produce. The reason being, the Marcellus around here produces what we call dry gas. Pure methane, or I'd say pure, it's 98% methane. Scrub out a little water vapor and you can put it right in a pipeline. In southwestern Pennsylvania, they can't. It's got too much what we call higher order hydrocarbons, propane, butane, all the way up to crude oils in it. That has to be removed before you can put it in a pipeline. The reason being they liquefy too easily, and liquids in pipelines are bad. They put out pilot lights, they destroy compressors. If you're compressing a gas or your air compressor, suck a bunch of water into it and see if you can blow the head off it. Same analogy. You got to get the liquids out of these pipelines. You got to create what we call pipeline quality gas, and that's typically 1,000, what we call 1,000 BTUs, 1,000 cubic feet contains 1 million BTUs of gas. Most pricing is based on 1 million BTUs of energy. The wetter gas has more BTUs. If you can burn it without having to move it very far, it'll have more like 1,400 BTUs per 1,000 cubic feet as opposed per cubic foot. Got to watch the decimal points here. But in order to move it, to sell it, it's got to be pipeline quality. And so the stuff we have around here goes in the pipeline direct. Down here you got to process it. Nothing wrong with processing because everything you take out is valuable. And it's worth $100 a barrel, not $3 a thousand MCF for what we $3, $4, whatever we're currently getting for natural gas. So the liquids are now the current attraction because the natural gas, the methane, the dry gas by itself is just not worth enough to pay for all this drilling. Typical drilling costs to drill a 10,000 foot horizontal well, frack it, probably $3 million, maybe $4 million. That includes its share of the well pad and the road. That's part of the incentive, of course, to cluster these things. You can drill a pad and literally have 1 well per pad. That's what we did in the Black River. We found that if you drill off 1 pad, you may spend $300,000 or $400,000 building a 5-acre gravel pad, but that can accommodate a bunch of wells. I've added some here. You can add some more if you control all the acreage. If you don't control all the acreage, then the number of wells and the length that you can drill is constrained by your lease ownership. New York State has a rule as well that a drilling unit can't exceed 640 acres. So a couple of people have gotten creative and they've made each well a different unit. If they're a mile long, it's slightly under 100 acres. So there's creative ways to deal with that, but the Pennsylvania scheme, there have been units as much as 1,000 acres. You commingle all the production from whatever wells you drill. Most of the pads I've been on in Pennsylvania, we drilled 1 well and the rig went away. And it's like, that's not very efficient. Why are we doing that? Simply, they want to do that to hold the acreage. It's called holding the unit. And That's done because we really don't want to produce all this gas at present prices, but we want to hold this unit and the infrastructure so when the price goes up, we can go back and drill some more wells. This is one of the bones of contention of people that, everybody has a different perspective on this. Some people want to produce all the gas now and get the check. Other people, there's people say no, it'll be worth more in the future. You make the same kinds of decisions buying and selling animals, farm machinery, you name it. You know, do you want to take the money and run, or do you want a longer revenue stream to last a lifetime or longer? We don't really know the total life of what these horizontal shale wells are going to do. I've seen some of them that have been pretty well depleted in a couple of years of producing them at a maximum rate. Producing at maximum rate is not often desirable, not only from the money standpoint, but if you produce them too fast, you generate too much of a pressure gradient down here, you invite formation water in. Formation water is your enemy. We want to leave as much of it as we can down there. So there are pros and cons to producing them quick, producing them slow, operator type decisions, whether or not the pipeline will even take the stuff. So this is basically what the industry is doing at present. Bring that to, well, I should say a little bit about surface as well. When we set up a drill rig on this 5-acre pad, we've typically put down a couple feet of gravel. I was on a pad last fall where they bragged that they had set in 17,000 tons of shot rock for the road and the pad. Well, I don't know, I didn't do the arithmetic, but I'll bet you that's 500 truckloads just to get the pad built. They had to fix a mile of town road as well, and we've got a guy here who's going to talk a little bit about Pennsylvania roads in a bit, but had to fix the road before we moved the drill rig into the location because the road wasn't in very good shape. And you're basically bringing in over the road equipment